Hi there. In this video we're going to be using double integrals in both Cartesian and polar coordinates to show that the integral from negative infinity to infinity of e to the negative x squared dx is equal to the square root of pi. Let's get to it. So this is what we're going to show. Let's start by showing the integral is convergent. One thing you want to notice is that this is always bigger than or equal to 0 for all x. And also we have symmetry in the sense that if I just plug in negative x, I get the regular function value. So what that means is that if I look at the integral from 0, say to b, this is equal to this integral. Just by flipping it around. So we're going to use this to show that this is a convergent integral by starting with just the positive side. And one thing that you want to recall is that e to the x is increasing, which means that if x is less than or equal to y, then e to the x is less than or equal to e to the y. So this is an increasing function, and we're going to use this to do something else. So we're going to start first with x bigger than or equal to 0. And if I multiply on both sides, since x is a positive quantity, right, it's bigger than or equal to 1, if I multiply both sides of this inequality by x, the inequality is maintained. So I get that x squared is bigger than or equal to x. Now I'm going to multiply by negative 1. And since negative 1 is negative, the inequality flips. And I get that negative x squared is less than or equal to negative x. Again, this is for x values that are bigger than or equal to 1. So e to the negative x squared is less than or equal to e to the negative x for all x bigger than or equal to 1. Now we're going to use this, in fact, to get boundedness of the integral from 1 to infinity here, and we'll see how, right? So again, we have this inequality holding. And this is for x bigger than or equal to 1. So now let's look at the integral. So if I integrate 0, I'm still going to get 0. And here I'm integrating from 1, say, to b. So let's say for b bigger than 1. 0 is less than or equal to the integral of e to the negative x squared dx, which is bounded by this integral. And this is an integral that I can evaluate. So if I plug in b, and this is equal to, so simplifying here, this is maybe 1 over e minus 1 over e to the b. All right. So if I take the limit as b goes to infinity across, then we can use this sandwich theorem. And when I take the limit as b goes to infinity, this is the improper integral. And I've computed this here to be this. Now as b goes to infinity, e to the b goes to infinity, so this portion is going to 0, so this limit is just 1 over e And so this has to be some finite value. Now, another thing is that e to the negative x is continuous for all x values. So the integral from 0 to 1 is also some finite value. And now by using the symmetry then, first let me note this. So this is a convergent improper integral, and I'll just say it is some finite value. And so by symmetry, it's just 2 times that integral. And let's call this a value I. And so the point of the discussion above is that I is actually a real number, so I'll be able to do some algebraic manipulation with it. All right, now that we know that the integral in question exists and is right a finite value, the key idea is using double integrals in the following way. So if we look here, if I look at this square, which has side length 2b, then I have these 2 circles that are one that's inscribed and the other one which closes. And let's give these things names. So I'm going to give the inner circle the name D1, and let's write it. So its radius is b. So that's the description, and so that's everything that's inside of that circle, centered at the origin with radius b. Let's let the square, let's call that r. And you'll see that the square region is all x values that are between negative b and b, and all y values are between negative b and positive b. Now for the outer circle, what you want to see is that its radius is the square root of 2 times b, because this is a nice right triangle with side lengths b and b. So then b squared plus b squared is 2b squared, and that's the length of the hypotenuse. The square root of that is the length of the hypotenuse. So we can describe that region with this inequality. Okay, now the function that we're actually going to consider in 2 coordinates is actually the following. And we're going to be integrating this function over these regions. And what you want to notice is that if you give me any point x, y in the plane, this is always bigger than or equal to 0. Again, right, so for the same reason as we had before. And since this is a subset, so the inner circle, D1, is a subset of the square R, which is a subset of the outer circle, D2, we have this relationship between the double integrals. All right, so with this inequality, with this string of inequalities, I want to see how this is going to bear on the integral that we were interested in. So first, let's just examine this integral right here. So R is a nice rectangular region in Cartesian coordinates, so I can rewrite this in this fashion. Now, I can use the property of exponents. To rewrite it like this. Now, I'm going to be iterating with respect to x first, so and y, this expression then is constant with respect to x, so I can pull that out of the integral. Now, when I integrate this, this is also a constant with respect to y, right? This integral from negative b to b of e to the negative x squared dx. This is some constant. So I can pull that out of this integral, and we get this. All right. Now, if we allow b to go to infinity, I'll see that both of these will, I mean, these are the same integral, right? If you look here, right, it's just a change in the variable name. So let's write here that this is it's that integral squared. But so we note this, and now let's investigate the other two integrals, and this is where we're going to introduce our polar coordinates. So let's do that on the next page. All right, since those two regions, D1 and D2, are so similar in form, namely just the insides of some circles, let's look at another region, E. And so this D is really sort of standing in place for B and the 2B squared. But anyway, let's check this out. So this is the closed disk centered at the origin with a radius of D. So if I convert this to polar equations, this is expressed as the sort of pair r theta, so that r is less than or equal to D. Remember again, because x squared plus y squared equals r squared. I'll write that in a different color on the side. And so we can compute this integral. So I'm going to rewrite this once. So I can factor out that negative. And what I see now is that when I write this in polar form, let's write it over here. If I investigate the disk, then my thetas go from 0 to 2 pi. They have to traverse the entire circle there. And my radius is just going from 0 to D. And so we get our area differential. And now this is something I can integrate because I can do a substitution. So let's do a substitution. So these are two things for the substitution. And if you want to change the bounds of integration, I guess we can do that. So if r equals 0, u equals 0, and when r equals d, u equals negative d squared. So giving myself a little bit more room here. And we have to multiply by the negative half. Du d theta. Now I can integrate this. And I plug in my bounds of integration. Forgot the negative there. Oops. And this is just a positive half, right? So this is all right, so there are no thetas. So when I integrate, I just get a theta term, and I see that I just get a multiplicative constant of 2 pi. So let's see that this is equal to pi times 1 minus e to the negative d squared, which we can rewrite as pi times 1 minus 1 over e to the d squared. Okay, and now the d here was just to write some number according to the radius of that circle. And so if we look at our the regions d1 and d2, then I know what these integrals are, and I'm going to rewrite them over here. So that is the integral over the region d1 of e to the negative x squared minus y squared is pi times 1 minus 1 over e to the b squared. And the integral over the region d2 of e to the negative x squared minus y squared is equal to pi times 1 minus 1 over e to the 2b squared. All right, so now let's use these facts to finish off our result. All right, so let's summarize the inequality that we had. So this is the inequality that we've just established. And as I take b to infinity, what I see here is that the left-hand and right-hand side are both going to pi. So let's and so this limit, right, so b is going to infinity, so e to the b squared goes to infinity, so 1 over that goes to 0. And the same thing is true on the right-hand side. So I have that pi is less than or equal to the limit as b goes to infinity of that quantity squared, which is also less than or equal to pi. So this limit is equal to pi. And we've shown that the integral from negative infinity to infinity of e to the negative x squared dx is finite, and squaring is a continuous thing, so I can pull in the limit and now as b goes to infinity, this is our quantity I. Right, it's the integral from negative infinity to infinity, so therefore we have our result. Hope you found this helpful. Thanks for watching.